So I think if I summarize the very good presentation we had up to now, first of all, for a toxicologist, food is chemicals. It's a bit shocking, but it's a way to look at it. And this is not really a problem, except if we understand that actually all chemicals can actually produce toxicity, which means that we need to manage chemicals, and we need to ensure that the chemicals present in food are safe. And we can see with the principle of Paracelsus that it's those which make the poison. We have a clue on how we can do that. To actually ensure that chemicals are safe in our food, so we need to answer the question, how much is actually safe? And to answer this question, we need to understand all the toxic properties of chemicals, and I think this has been very nicely shown that you can formally do that. You have all these toxicological studies, different duration, dealing with different age, and dealing also with different duration, different endpoint, and you have a lot of data. But now it doesn't really tell you how much is safe for a human being. And actually you need to translate this toxicological database into value which are actually of relevance for human. And then with this value you can then compare to exposure, and this is the process of risk characterization. But the process of establishing the safe level of exposure or this value for human is called Hazzard Characterization, and it's what I will talk about now. I think it can be relatively complicated. I think you will probably, you don't need to keep everything in your head, but I think it's very important to know once what is behind an acceptable daily intake. So as we have seen, we have plenty of data coming from the experimental data, or sometimes we have human data. So the first step in the hazard characterization is actually to collect, to review and analyze all this data. And, you know, which is, if there are human data which looks adequate, this will be preferred. And sometimes there will be mechanistic data, so we will know how the chemicals are actually acting, and sometimes we even know, and we had some example cited previously, where there are mechanisms which are just specific for an animals and which will not be relevant for human, and in that case, this type of study would not be used for a risk assessment. I think this hazard identification step will provide two types of fundamental information. The first one, it will tell us if we assume, if we can assume that the chemical will act through a threshold mechanism. It means that for such chemicals, we know that we could establish a dose below which there will be no risk for the human being. So it's a threshold approach. Otherwise, and we will see that later, we will consider that we will assume, even maybe there are threshold, we will assume that there is no threshold. And the second very fundamental information we will get is actually the definition of what we call the pivotal studies, which is the studies the most important. And in general, this is based on animal studies. And we don't really know whether they are relevant for human because there is not enough comparative data, but we use actually some conservative assumption. So we assume, for instance, that the toxicological effects which are seen in animals are actually relevant for human. We use very high dose in animal studies, and we estimate that it will be relevant for low dose exposure in human. And we assume also that the mechanisms which are involved in animal studies are actually relevant for human. And in general, what we get, what we use, if we don't have any other reason, we don't have reason to do differently, we use the most conservative studies which will cover all the effect of the database. So then, as I said, we can define whether we have the pivotal studies and we know whether it acts through a threshold or not. So the fact that we differentiate between threshold and not threshold is important because we apply different process to the data to get the value for human. For the threshold effect, we will use the NOEL that George was telling about, and we will divide it by uncertainty factors. I will get back to that. And for non-threshold effect, we cannot do that, so we will do a quantitative risk assessment. I will get back to that. Now for the threshold effect, what does it mean? In a study, in the pivotal study, the most conservative one, you have a dose response like here in animals, and then you get the NOEL. And then you need to extrapolate to human. In general, you don't know exactly how to do that, so you just use a factor. So you divide the NOEL by a certain factor. And then you get, an answer for the mean human, the average human. But we all know that there are differences probably in human. It's not necessarily known, but we expect like children would be more susceptible, or pregnant women, or elderly. So we add another factor here to just deal with the inter-individual variability within the human population. So by using these factors, we get an ADI, which is the acceptable daily intake, which is a safe level of exposure in human. So what are these factors? So actually, in general, when we start with animal studies, we have a factor of 10 in general, which is devoted to deal with the difference between the test animal and the human. Actually, these factors deal with kinetic differences, so which mean that differences between absorption, elimination, between the test animal and the human, and also dynamic, which more refer to the sensitivity of the target cells. And then we have also a factor of 10 to deal with the human variability, and it's also about kinetics and dynamics. And so the ADI is the NOEL in general divided by a factor of 100. Sometimes you have additional factors which deal with inadequacy of the toxicological database. For instance, you don't have a chronic toxicity study. So in that case, you have only subchronic, so you would add a factor to deal with this inadequacy and this uncertainty. So what does it mean, the acceptable daily intake? So the official definition is the following. So it's an estimated amount of a substance expressed on a body mass basis to which a human subject may be exposed daily over lifetime without appreciable health risk. And I think there are several words which are very important here. First of all, I think it's a human, so it's basically deal with human, so it's a safe level in human, may be exposed daily, so every day, over lifetime, so during the whole life. And without appreciable risk. It's wording which is a bit bizarre maybe, but I think it's taken into consideration that scientists don't like to be sure about safety and don't feel comfortable saying this is an absolute guarantee and safety. But it means that if there is a risk, it's non-appreciable, so you cannot measure it, and it's basically what it means. Who is actually establishing ADIs? So it's recognized an independent expert group. So there are supranational organizations, like we heard already about WHO, FAO expert committee, one on food additive, for instance, and contaminant, one on pesticide. But you have other organizations like the European Food Safety Authority, and you have many national authorities, the US FDA, US EPA, in Germany also, in Australia, and many. Importantly, the ADI applies to the whole population except infant under 12 weeks of age. And interestingly, it's applicable to any food chemical, not only additive, but also pesticide, veterinary drug, contaminant, mycotoxin, etc. And importantly to understand is that the ADI covers all sources of exposure, which means that if you need to assess the safety based on an ADI of a contamination of a product, you need to understand what are the other contributions of the diet. So maybe a remark about unit. So the ADIs are expressed in milligram per kilogram body weight per day, and the kilogram body weight refers to the consumer. So you use then, if you need to know, for instance, the total exposure, which is acceptable, will multiply that by the body weight. So if you have 1 milligram per kilogram body weight per day, 60 kilo person, this would be 60 milligram allowed for, in average for a person. And the ADI are established based on animal data expressed in milligram per kilogram body weight per day. In that case, obviously, the kilogram refer to experimental animals. And all this should not be confused with, for instance, concentration of chemical in experimental diet of toxicological studies, which are expressed as milligram per kilo. Sometimes it's said there is toxicity at 3 milligram per kilo, which means 3 milligram of kilo of diet. You need to know how much the animal will eat and how much it will weigh to be able to have the exposure. Level in food, analysts will analyze food and express sometimes their data in milligram per kilo. It's the same thing, and usually a regulatory limit will be also in milligram per kilo. Should not be confused with the ADI. Now, just a quick example. It's a pesticide. You see that it's not genotoxic, and you see that it has been tested in several experimental systems. In that case, the most relevant data was this, a 2-year study in rat, 1.8 milligram per kilo. And this is the most conservative. There is also cancer, but at higher doses, which is related to the toxicity produced at lower doses. So this one is the most relevant and was used to set up an ADI. In that case, it's rounded. And since it's not very precise, to round is not a problem. So sometimes you will look for ADI and you will not find ADIs. Why? Because there are similar concepts, I mean, same concept, but with different name. And for instance, for some contaminant, you will not have an acceptable but more a tolerable daily intake. But it's the same thing. And I just think about these radioactivity things. For instance, there is a tolerable daily intake for uranium, for instance, which has been set by EFSA several years ago, for instance. For chemicals which accumulate in the body, where the body burden is quite important, the safe level is actually expressed on a weekly basis and sometimes even on a monthly basis. So weekly basis, for instance, ochratoxin A, for instance, cadmium, or monthly basis you have dioxin-like compound, for instance, which are on monthly basis. Sometimes you have group ADI. If you know that chemicals will occur in group and they will have the same target, same mechanism, so the effect will be additive. In that case, you will have a group ADI. And you have as a name, you know, temporary ADI when some data are missing. The US EPA has another name, it's reference dose, which should not be confused with the acute reference dose, which is some sort of an ADI, but for very short-term exposure. Now, yeah, the GRAS status, I think, has been discussed already. Now, just something about essential element. We know, like vitamin A, they can create toxicity, so you will have also for essential element dose response related to toxicity, but then to establish a safe level of exposure, you need to be very careful not to apply uncertainty factor blindly, because otherwise you will just get in a situation where you don't get enough of the micronutrient, and you need to understand that you need also to ensure that you are out of this deficiency curve. So you need an exposure which is not higher than this, but not lower than that. It's why for that kind of chemicals, you have recommended dietary health-based guidance value dealing with nutrition, and you have tolerable upper intake dealing with toxicity, and both need to be compatible. And sometimes the difference is not that big. Important again in terms of unit. First, there are different value for different age, and the unit are in milligram per person per day, and not per kilogram body weight. So, now what about quickly about non-threshold effect? So the potential to cause cancer through DNA reactive molecules, so molecule which bind to the DNA is the main example. In that case, we assume that no safe level exists. One molecule can increase the risk. In that case, we cannot have a safe level, and we apply quantitative risk assessment. And sometimes we can actually establish what we call a virtual safe dose, which is a level of risk considered tolerable. And this level is set up as a management decision. And very often we have the 1 cancer per million of exposed people over lifetime, which is used as this kind of virtual safe dose. And this quantitative risk assessment looks interesting because we can quantify the risk, but actually does not really quantify the risk because it required extrapolation over a very large range of dose. Most of the dose are actually out of the experimental dose, so it's very inaccurate, and there is no adequate simulation of the carcinogenic processes. So meaning that in the end, the numerical risk estimate is more influenced by the selected mathematical model than the actual data. So the applications are limited. Very often we use the linear dose response. It's clearly over-conservative, but I think we all know that. And I think it can be helpful to do risk ranking and to set up priority and sometimes assess the impact of mitigation measures. Now, something I have not said is that now there is emerging, and I think I want to quickly talk about that. It's the benchmark dose because it's more and more used at WHO, EFSA, and this. So the benchmark dose is actually a modeling also, but it's modeling within the range of experimental data. And then we calculate a dose which correspond to a certain response. And in general, if it's based on animal studies, we will use like 5% response or 10% response. And if you take the lower bound 95th percentile, you will get something which from a safety perspective is very similar to the NOEL. And it's an alternative approach which is used more and more because it takes into account the whole shape of the dose response, which is quite important, and extract much more from the data. And it can be applied to genotoxic carcinogen and other chemicals. So it's kind of an harmonization of all this. So how is it used? Actually, for threshold effect is used like an OL. So then you divide the benchmark dose by a factor of 100, and you get a safe level of exposure. Now, for non-threshold effect, it's not a measure of risk, but we can also use more and more, and I think probably Paul Hepburn will talk about that. You can actually divide this benchmark dose by a factor, by the exposure, and then you get a margin of exposure, and this margin of exposure allow you to actually establish the level of concern and see whether you need management option. And EFSA said that if you have a margin which is higher than 10,000, it's probably not a big priority to work on that. So last slide, hazard characterization. What are the outputs? So when we have threshold effect, so we have safe level of exposure which are established. It's health-based guidance values such as the ADI. It covers the lifelong exposure to the chemical, the whole population except a very, very young infant. It's a safety assurance process, so there is no quantification of the risk. It's a very easy tool to manage chemical in food, and you can answer questions such as, is exposure to a chemical safe or not? Or how much of a chemical can be accepted in a specific product, for instance. But the ADI is not actually a threshold of effects, so meaning that if we have short-term excursion above the ADI, we don't really know what it means, but it's unlikely that there will be concern, and this would require a case-by-case approach. And it's, as I said, it's applicable to any chemicals, for non-threshold effects, the hazard characterization does not allow really to characterize the risk, but actually it's allowed to establish level of concern, risk ranking or comparison, and allow to set up priority and get impact on mitigation measure. So I think I will stop here, and I thank you a lot for your attention.